there we go. All right, where was I? I don't remember. I have to start over from the beginning. What? Oh, okay, yeah. I have to start over from the beginning because I lost my train of thought. So we just finished the pits of chapter 6. All the calculations. You saw some of you who already had lab today and did EMS. There were some calculations and looking at the simulations, the PhET simulations about how we, as scientists, made up a model of an atom that reflects what we actually observe. That's the big thing there, that we could no longer just think about electrons as particles. We actually also have to think about them as waves. And so at the end of class, because it is Thursday and I need to ask you some type of paperclip question because I've made that trend now. I'm going to ask you if you could choose, if you had to choose to be a particle or a wave, you can only choose one. So you're not like an electron where you can be both at the same time. You have to choose one, wave or particle, all right? Because that's what we learned about in the beginning of chapter 6. So now that we're done talking about the atom and the electron, we're going to kind of skip around and look at some details about molecules themselves. We're still thinking about electrons just kind of in a more broader scope. In chapter 6, we left off on Tuesday talking about valence electrons. Once we start putting electrons in orbitals, remember our orbitals are S, P, and D, basically the solutions to the Schrödinger equation. We oftentimes only care about the outermost electrons. We call those the valence electrons. There are some tricks into determining valence electrons. I have here, in general, they're the outermost electrons. So for main group elements, it's real easy. S and P block elements, they're just, it's just the group number. And then it's a little hairy for transition metals. But we're going to focus mainly on the main group elements here in this next part of the chapter. So we are going to electron tunnel to chapter 7. All right, so if you haven't already downloaded the chapter 7 slides I posted earlier this week, we're going to go there. Right, and so for fun, I use the term electron tunnel. Electron tunneling is a wave property of electrons, in case you care. We actually do interact with electron tunneling every day. Anytime you plug in an electronic device into an outlet, electron tunneling occurs. It's where an electron basically overcomes a seemingly impossible potential energy barrier. Metal oxides that form on the outside of like plugs, you know, like anything that's metal, that's exposed to air will form metal oxides on the outside. Metal oxides are insulators. So do they conduct electricity? No. And so all of our plugs and stuff, they have these thin coatings of metal oxides on them, but they still, when we plug them in, they still work. And it's because electrons are tunneling through that barrier, basically. So we've electron tunneled from chapter 6. We're still talking about valence electrons. We're just going to do some interesting stuff with them now. I want to go into chapter 7 because it'll help you for your lab next week. And in the end, it doesn't matter what order we do this in. It's all going to be assessed on midterm 2 anyway. So we talked about valence electrons, all right? Those are of atoms. But the thing is we don't interact with atoms like on a day-to-day basis. We interact with molecules, things that are bonded to one another. So how we can predict how things bond to one another, we can look at what's called the octet rule. So Gilbert Newton-Lewis came up with this idea of how to predict how atoms act and behave to form molecules. So the octet rule simply states that atoms will tend to gain, lose, or share electrons to gain an octet, basically meaning 8 valence electrons. For the majority of elements, but for hydrogen, hydrogen only needs 2 valence electrons to have a complete octet. That octet is significant because it basically means that your highest n level is completely filled. When we completely fill things, things tend to be stable. So that was basically Gilbert Newton-Lewis's thought, was atoms will tend to want to either beg, borrow, or steal their way to a stable shell. And so we'll explore the different ways atoms can do that. So the goal here, 8 valence electrons. So one of those ways is through sharing of electrons. That's covalent bonding. Those are the Lewis structures we're going to draw here real soon. All right, so in this slide, you see a bunch of different elements kind of based upon where they are on the periodic table, but take note in the dots around each element. Those dots represent the valence electrons that, we could, figure out from the periodic table. But you can clearly see, okay, what are the different ways an element can achieve an octet? Over here on the right side, oh, stupid pen, give me a second. On the right side of the periodic table where our metals are, those elements tend to just lose their electrons, right? Like sodium, when you encounter sodium in a compound, it's usually something like sodium plus, sodium chloride. So that's why metals tend to lose electrons. Over here are noble gases. They already have fulfilled octets. If you count the dots, there's 8 dots. There, they tend to not form chemical bonds because they already have very stable, full octets there. So metals lose electrons, usually form an ionic bonds. Noble gases, they already have octets. All right, these in red, these elements typically exceed their octets. These are exceptions that we'll talk about later, so we're just going to ignore those for now. Where we actually want to focus on, that'll help us with Lewis structures, or what I have highlighted in green right here. Based upon their valence electrons, we know carbon has 4 valence electrons because it's in group 4. Nitrogen has 5 valence electrons because it's in group 5, etc. The octet rule works really, really well for these elements. And then those in red here, we see some exceptions that we'll explore. All right, so these atoms, hydrogen, carbon, nitrogen, etc., we can draw their Lewis structures, and that's what we will do. There's a very systematic way to do it, and if you follow my 6 steps, you will always be right. All right. Okay, we're gonna skip this slide. We're gonna go to slide, this one, 11, covalent bonds. So we're gonna draw Lewis structures here. These structures are between all nonmetals. So what I had in green, all those green elements, carbon, nitrogen, oxygen, fluorine, all nonmetals. So covalent bonds, these are made by sharing of electrons within our non-metal containing compounds. And so I just want us to understand how covalent bonds are formed. When 2 atoms share electrons, we form a covalent bond, meaning one electron comes from one atom, the other electron in the bond comes from the other atom. So in a single bond, 2 electrons are shared between 2 atoms. So basically, this chlorine is combining with that chlorine, all right? And then what's highlighted here between these 2 these 2 circles, that's our covalent bond. But the thing is chemists are lazy. We don't want to draw all those dots around those chlorine atoms. So instead of representing a bond as 2 dots, we represent it as a line. So a line between those 2 atoms represents a covalent bond, but you need to recognize that there are 2 electrons in that line. 2 electrons make up a covalent bond, a single bond. All right, and so, just kind of going off of a trend here, if a single bond is 2 electrons, made up of 2 electrons, a double bond is made up of 4 electrons. All right, so very good. So here, if we look at the Lewis structure of CO2, we see that carbon is double bonded to 2 different oxygens. So each of those double bonds have 4 electrons each. So each line still represents 2 electrons, but since we've drawn 2 lines between 2 atoms, that represents a double bond, 4 electrons being shared. All right, a triple bond. How many electrons do you think are in a triple bond? 6, so same idea. So 6 electrons between 2 atoms as our bond order. This is what that's called, single, double, triple. As bond order goes up, typically the length between atoms gets smaller. Also, the strength between the bond gets stronger as you're sharing more electrons. So let's go with this trend here. What do you think a quadruple bond is like? How many electrons are there? 8, very good. So that's what I studied in my graduate studies. I made molybdenum quadruply bonded compounds. So I shoved 8 electrons between 2 molybdenum centers. All right, and so you might think, oh, four bonds, that must be the max. No, actually, there are quintuple bonds out there as well, and I think that is the max. I think that was like made, I think for the first time in like 2009, I think, a quintuple bond. These things are real unstable, but they're cool colors. That's why I like to study them. Okay, all right, so that's that. Okay, cool, covalent bonds. All right, we're gonna skip to slide 18. Perfect. Okay, so we're going to draw Lewis structures. So the thing is, for these Lewis structures, is they are always all nonmetals. All nonmetals, so all covalent bonds. We're drawing covalent bonds between all of these different atoms. So here are the 6 steps I was talking about. Master these 6 steps. So I'll just describe them, but I think it's best if we just practice it. So the first step, typically you're given a compound. So for example, you're given a compound like NH3, right? Okay, and then I'll say something, draw the Lewis structure of NH3. So the steps are, you need to count the total number of valence electrons in all the atoms in that compound. We know how to do that. We know how to count valence electrons now. So we know how to do that now. Basically, that total number of valence electrons is how much you are allowed to spend when you draw your structure. Remember, electrons, they can live in bonds between atoms, or they can live on the outside as lone pairs around the atom. So the number of dots that I draw, it really matters. I'm only allowed to spend so many, all right? And we need to make sure when we spend them that we obey all the rules. All right, so that's the first step. The second step, if there's a charge on the molecule or the ion or whatever, you need to adjust your valence electron count based upon that charge. So if it's an anion, you add more electrons. If it's a cation, you remove electrons. So for NH3, because it's neutral, do we have to adjust for charge? No, we don't. Okay. The next step is you draw the skeleton structure. So you need to identify the central atom, and then you draw all the other atoms in the compound, in the formula around that central atom. You draw all the atoms around it, and you draw a single bond between every single atom. So once you draw single bonds, how many electrons do you spend per bond that you draw? 1 electron? 2 electrons. Yeah, so we need to keep track of how many electrons we spend. So the question is, well, how do I know what the central atom is? It's almost always the first element that's written in the formula. So what do you think the central atom is in NH3? N, yes, it is, because it's the first one written. Okay, and then finally, once you have the skeleton structure, you keep track of your electrons, distribute any extra electrons you have on the outer atoms first, making sure to complete their octets. Then if you have any extra electrons remaining, then you put them on the central atom. Only if you have electrons remaining. I remember when I was in high school drawing Lewis structures, I would literally take my pen and just draw dots around things and not keep track of any electrons. I would just keep drawing dots, or I not keep track. So let's not do that. We need to make sure we keep track of our electrons. And so once you focus on the central atom, you need to go back and look at the octets of all of your atoms. If your central atom is still electron deficient, we need to start making double bonds. And I'll show you examples of that. So let's get started. So our first example. Oh, here are some tips. And I don't really want to talk about these. Okay, I will. So here's some tips. If hydrogen is in your formula, based upon the dot structure of hydrogen, how many bonds do you think hydrogen can make? Just 1. Yeah, because there's only one electron on it. So basically hydrogen can only make a single bond. So that's kind of a nice tip. Also, hydrogen will never be the central atom because it can't make more than 1 bond. And then fluorine and chlorine, our halogens, also work that way as well, because there's only 1 remaining electron there. Fluorine, chlorine, our halogens will also make 1 bond if they're the outer atom. And you can kind of see how the dot structure is analogous to that of hydrogen. There's just like 1 extra dot. And then we'll talk about these exceptions later. All right, so let's do our example, ammonia. Who's done a Lewis structure before? Okay, a lot of people. All right. So hopefully my tips, my steps agree with how you learned it. But I remember in high school, I don't know. I just would draw the thing and I would draw dots and I would never know when to stop. So hopefully with these steps, you know when to stop. So here's the strategy. I've just kind of condensed it. So the first step, we need to count up valence electrons. So we're doing ammonia. I like to just take inventory. There's 1 nitrogen. So how many valence electrons do I get from nitrogen? It's not something you need to memorize. It's all right on the periodic table. So how many valence electrons come from nitrogen? 5, yes. And then what about hydrogen? 1 valence electron, because nitrogen is in group 5A, hydrogen is in group 1A. But then there's how many hydrogens? 3. All right, so it's 3 times 1. So I can spend 8 valence electrons, and that's it. That's it. So that's step 1. Adjust for charge. Do we need to do that? No, because ammonia is neutral. Now we draw the skeleton structure. So we need to identify the central atom, which is nitrogen. And skeleton means we draw all the other atoms and single bonds to it. So I have 3 hydrogens. It doesn't really matter where you put them. And then you draw single bonds to the central atom. So how many electrons have I spent so far? 6, because there are 1, 2 electrons in each of those bonds. All right, so I spent 6 electrons. I'm allowed to draw only 2 more electrons. That's it. Okay, yikes. So there's the skeleton structure. Next is you place electrons on outer atoms first to complete octets, to complete the octets. So these hydrogens, do they have complete octets? Yes, yes, they do, because hydrogen is the exception. So if we look back at the octet rule, it's 8 valence electrons for majority of elements, but hydrogen actually only needs 2. That's the hydrogen exception. Hydrogen only needs 2. Basically, just draw a single bond to hydrogen and it's happy. Okay, where am I? Right here. Okay, so hydrogens, they have complete octets. So where am I going to put those 2 electrons? Where am I going to put them? On nitrogen. Yeah, because that's the next step. You place on central. That's it. Boop. That's it. Okay, so I spent all my money. Now we need to check octets of everything. So are hydrogens happy? They are. Is nitrogen happy? Does it have a complete octet? Yes, it does. 1, 2, 3, 4, 5, 6, 7, 8. So there we go. That's ammonia. All right, so we didn't have to do step 6, double bonds if needed. That's the next one. Okay, was it that bad? Not that bad? Okay. I love when there's steps and you follow the steps every time and you're right. So let's bring these steps down here and do formaldehyde. So let's get valence electrons. We have a carbon, we have 2 hydrogens and an oxygen. So carbon gets how many valence electrons? 4, and then hydrogen 1, but there's 2 hydrogens, so 2 times 1, and then oxygen gets how many? 6. So that's a total of 12 I'm allowed to spend. Okay. So I have formaldehyde here, and I'm explicitly telling you that carbon is the central atom, but you can also see it in the formula here. So I'm going to put carbon in the center. I'm going to put oxygen up here. Again, it doesn't matter where you put things. Hydrogen to the left and another hydrogen to the right. Skeleton structure means we have to connect everything via single bonds, single covalent bonds. So I draw a line. 1, 2, 3. Okay, I can bring that hydrogen a little bit closer. There. Okay, how many have I spent so far? 6. So I'm allowed to place 6 more. So where am I right now? I did valence electrons, adjust for charge, skeleton. Okay, now we place on outer atoms first. So, and I have 6 more electrons to place. So do I put any electrons on hydrogen? No. Where do I put them? On oxygen. Yes, we always place on outer first. So I already placed 6 electrons. So 6, 7, 8, 9, 10, 11, 12. Those are all my electrons. Those are all my electrons. Okay. So I can't place any electrons on the central atom, essentially. Okay. So now this is the last step. We need to check for octets of everything. And if our central atom is electron deficient, then we need to start making double bonds. So hydrogens are happy. Is this oxygen happy? Does it have an octet? Yes, it does. But does that carbon have an octet? No, it doesn't. So if you were me in high school, this is what I would have done. I would have gone boop, boop, and just added 2 more electrons there. Now carbon's happy. It has an octet, but what's wrong? I put too many electrons. I overspent. All right, that's what I would have done. And I clearly remember doing this in high school, and like no one corrected me. So I'm here to teach it correctly here. Is when we get to this step and we see our central atom is electron deficient, we do not just add more electrons. We cannot. So what we're going to do is just move around the electrons we already have on the structure. So this is what we're going to do. How many more electrons does carbon need? Just 2 more. So I'm just going to take these, these electrons on oxygen, and just instead of making it just solely on oxygen, I'm going to make it make a double bond to carbon. All right. And so if I redraw this, H, carbon, H, double bond oxygen, how many lone pairs are still on oxygen though? Once I just move 1 lone pair, there's still 2 lone pairs there. Yes. So now look at carbon. Does it have a total of 8 electrons around it on its octet? Yes, it does. Does oxygen still have 8 electrons around its octet? Yes, it does. All we did was rearrange the electrons that were already there. All right, and if you look closely, there are still 12 electrons in that red structure. This is the correct structure of what is this? Formaldehyde. Okay, so those are the steps. They work every single time. All right, so now let's talk about formal charge, because there's some specific rules on how to make the double bonds. And this is where me and your book disagree on things. So if you read the book, who reads the book? Okay, all right, not everyone lie at once, that's fine. This is where me and the book disagree. They don't actually teach formal charges, which is wrong. So I'm here to teach you correctly. So formal charge is we can inspect every single atom and basically predict how double bonds need to form to make the most valid and stable structure. So what a formal charge is basically we're like pretending the atoms themselves are like ions in a sense. So how we can calculate the formal charge of an atom in a structure. This is the important thing. We're calculating the formal charge of an atom that's already drawn in a structure. Is we take the number of valence electrons that the atom should have off of the periodic table, and we subtract the number of electrons that are actually on that atom in the structure. So we only count half of the bonding electrons, but we count all of the non-bonding electrons. So this means lone pairs. All right. So there's the formula to calculate formal charge. I think it's better if we just do it. The trick is I like to memorize formal charges once minus has. Formal charge is how many electrons an atom wants based upon the periodic table minus how many it has in the Lewis structure. But I will point out that calculating formal charge is different than octet. That's commonly a mistake there. So once you calculate formal charge of your atoms, your correct Lewis structure will always minimize formal charge, where formal charge of 0 is preferred. Or if you have to have a negative formal charge, it is on the most electronegative atom. Okay, I know there's a lot there, so let's just practice it. Okay, so let's check the formal charges of all the atoms in our previous 2 examples. So let's look at ammonia and formaldehyde. Formal charge is once minus has. So you only want to count half of the electrons in every bond. This is basically how I do it. I remind myself, okay, a bond is made up of 2 electrons. I'm going to re-split the bond. I'm going to say, okay, there's 1 electron assigned to hydrogen. There's 1 assigned to nitrogen. And then I'm going to do it again here. There's another one on nitrogen. There's another one on hydrogen, nitrogen, hydrogen. And so I can focus in on nitrogen and think, okay, these are all of the electrons assigned to nitrogen. So how many electrons are in that red box? 5. Yeah, so I only counted 1 electron from every bond, but I did count both that are on that non-bonding pair, that lone pair. So there are 5 electrons on that nitrogen. How many on each of the hydrogens? Just 1. So this is how we calculate formal charge. Remember, formal charge is once minus has, where once comes from the periodic table. So let's do nitrogen first. Nitrogen wants how many electrons off the periodic table? or typically nitrogen has a valence shell of how many? 5. Yeah, so nitrogen wants 5. How many does it have in this structure? How many are in the box? 5. Yeah, so 5 minus 5. So that's 0. 0 is good. A formal charge of 0 is good. Okay, so let's do hydrogen. Hydrogen typically has how many valence electrons on the periodic table? 1. And then in this structure, how many electrons are on the Lewis structure? 1. Yeah, so it's 1 minus 1. The formal charge of hydrogen is 0. So if you go through all of the atoms here, every single atom in this Lewis structure has a formal charge of 0. Is that good? Yes, that is good. Zeros are good when it comes to formal charges. Okay, so let's do this one. Let's do this one. So again, you take every bond, you split up the electrons, so each atom gets 1 electron in the bond. So remember, a double bond has 4 electrons, so 2 each. All right, so let's do oxygen. Wants minus has. Oxygen has how many valence electrons off the periodic table? It's in group 6. 6. Okay, minus how many electrons are assigned to oxygen in this Lewis structure? 6. I'll show you. 1, 2, 3, 4, 5, 6. Right there, right there. 6. So 6 minus 6. Oxygen has a formal charge of 0. Is that good? That is good. All right. All right. Formal charge of hydrogen. It is also 0 because there's only one. There's 1 electron. This one's also 0. What about the formal charge of that carbon? Also 0. So carbon typically has 4 valence electrons minus, if you count here, 1, 2, 3, 4 electrons on that carbon, so 0. So everything is 0. That's good. Those are correct Lewis structures. Now let me show you some examples where it's not so, where we actually have to use Lewis structures to decipher what is correct, what is the most valid Lewis structure. So let's do this one, carbon dioxide. So hopefully you don't know what this looks like already, or do you? Do you know what CO2 looks like already? Okay, so in your mind, just forget for a moment what it looks like, and let's just go through my 6 steps. What's the first step? Valence electrons. And I already have those here. So there's a carbon, 2 oxygen. So what's, how many valence electrons am I allowed to spend? 16, thank you. I'm not good at math. 16. What's the next step? Valence electrons. Charge. It's charge. Do we have to adjust for charge? No, because CO2 is neutral. What's next? Skeleton. Yeah. So what's my central atom? Carbon. Yeah. So carbon, and draw in some oxygens there. Boop. There we go. Okay. I've spent 4 electrons already. Okay. So again, just follow my steps. Don't think about what CO2 looks like because the steps work. So I already drew 4 electrons. So now what do? I put electrons on the outer, so oxygens first, making sure I complete octet. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. Do I put any electrons on carbon? No, because I ran out of electrons. Oh, but do I want to so bad? Because if you look at carbon, it's octet deficient, isn't it? So that's a problem. That's the last step, right? The last step is check all the octets. If your central atom's octet deficient, start making double bonds. So we're at that step right now. We've finished spending our electrons. We need to make double bonds. So let's just kind of think ahead here. Carbon right now only has 4 electrons on it, so I need to give it 4 more electrons. So how many more bonds do I need to draw towards it? 2. Yeah, so if I make 2 more bonds to it, I can complete its octet. But here's the trouble. There's a couple ways we can do it, technically. Our brains want to automatically do this, right? I'm not allowed to just place more electrons on carbon, all right? That's what high school Lisa would have done. But don't do that. We just want to rearrange the electrons that are already there. So our brains want to do this, right? Where we put double bonds. We put double bonds to each of the oxygens to carbon. So it looks something like that. That's what our brains want to do. Yeah. But technically, there's another way we could do it too. Couldn't I do this? Carbon just needs 2 more bonds, but so could I do this instead? I could move that lone pair down, and I could move that lone pair down. Couldn't I also do that step in green also? So the green step, if I just move 2 electrons from one oxygen, it would look something like this. All right, and you know, if you're smart here, you might think, well, it can't be that one. It can't be that one. It can't be a triple bond and a single bond on the other side. Why not? Look at it. Check every single atom in both of those structures, the red one and the green one. Is anything octet deficient? Is there technically anything wrong with it? So this oxygen, does that have a complete octet? Yes, 2 bonds, 2 lone pairs. Carbon, complete octet? Yes, 4 bonds. Oxygen has a complete octet? Yes, it does. Does that oxygen technically have a complete octet? Yes, it does. 1, 2, 3, 4, 5, 6, 7, 8. What about that oxygen? 8. Technically, both of these structures obey the octet rule, but one of them is wrong. What do you think we need to do to figure out which one's wrong? Formal charges, the thing we learned in the previous slide. Dang it. Yes, so we got to get formal charges. So once minus has. So I'm just, this is nice and easy if you just put the structures right here. Remember, it's once minus has. You just subtract those 2 numbers and you get formal charge. So oxygen wants how many electrons on the periodic table? 6. Yes. What about carbon? 4. Yeah. So it's 6, 4, 6. And then again, on the other structure, it's 6, 4, 6. Those are the numbers that just come straight from the periodic table. Now we look at the structure and think about how many electrons are assigned to each atom in the Lewis structure. So again, meaning that we split each bond and make sure each of the electrons only go to one atom. All right, so I like to draw it like this. All right, so if I draw a box around this oxygen, how many electrons are in that box? 6. Yes. What about the carbon? If I draw a box around carbon? 4. And then that last oxygen, it's symmetric, so it's 6. So you see the formal charge in what we think is the correct Lewis structure of CO2 is 0, 0, 0. That's good. So let's look at the wrong one. The wrong one that technically still obeys the octet rule, but is technically wrong. So this oxygen right here has how many electrons assigned to it? 7. Yeah. So remember, this bond gets split up. So there's 6 total lone pair electrons, 1 coming from that bond. So it's 7. Carbon still has 4, but this oxygen over here has 5. So 6 minus 5. So we see when we get formal charges, it's -1, 0, +1, and that is not very favorable. So that's why CO2 doesn't have a triple bond on one side and a single bond on the other side. All right. But I don't want you to just think about your biases and be like, oh, of course, I knew that. Like, of course, it's a double bond. Duh. But no, formal charges actually describe why it's the double bond structure over the other one. Because technically both of them, they obey the octet rule. We have to look at formal charges to figure out which one's correct. And so we won't go into the nitty gritty. I'll do 2 more examples later where we have to inspect formal charges. Oh, like PO4 3- in the textbook. Oh, I like threw up when I saw it in the book, but it's okay. None of you opened the book anyway, so it doesn't matter. But we'll look at that later. All right. So I told myself to skip to slide 30. So we're going to electron tunnel again. We're going to become waves. And we're going to electron tunnel to slide 30. I forget what's on slide 30. Oh, okay, yes. Okay. So please practice the 6 steps to Lewis structures. It works every time. You don't have to just take a leap of faith and hope you stop drawing electrons at the right time. That was me not too long ago. So we'll look at some of the exceptions for Lewis structures. The first one, boron as a central atom. Boron is small enough that it is satisfied with 6 valence electrons. So just do memorize that. Also beryllium. Beryllium is okay with 4 valence electrons. right? So BF3, this is a common molecular compound. This is absolutely okay. So if you look at boron, you'll see like, oh, it doesn't have an octet. It only has 6 electrons. That's okay for boron. Beryllium, the same thing. BeF2 with no lone pairs on beryllium is a good, a valid structure. The second one, so you can be asked those questions. Boron trifluoride here, I could ask you the Lewis structure of that substance. The second exception here is odd number of valence electrons. So here's some examples. NO2, if you do the valence electron count, you get their 17 valence electrons. If there's an odd number, you cannot, it's physically impossible to have all complete octets. So you will never be asked an odd number of valence electrons. Us mere mortals cannot just use the 6 steps to solve that Lewis structure. So we can't ask you those, right? If there's an odd number. So that means if you're doing your work, you're doing your Lewis structure stuff, and you count an odd number of electrons, you probably did something wrong, because I'm not going to ask you an odd number of valence electrons because you can't solve it. Okay, so keep that in mind. Keep that in mind. All right. And the last one, the third exception here that you can actually solve is period 3 elements as a central atom. So over here on the right, you see some pretty gnarly molecules. These molecules, if you look at the sulfur, does it have an octet? Are there only 8 electrons around it? No, there's a bunch of electrons on it, but that's okay. For period 3 elements and heavier, so like sulfur, phosphorus, they can have expanded octets. We call this hypervalency. Just know that these essential atoms, it's just okay. We can still follow the same 6 steps and it'll work. And I'll show you some examples. So SF6 is an actual molecule. There are 48 electrons to place. Xenon tetrafluoride is also a molecule. You may be thinking, well, xenon, isn't that a noble gas? Like, they don't make molecules. Typically, xenon is big enough where basically its valence electrons are so far away from the nucleus that they can participate in chemical bonds, chemical reactions, if paired with a really electronegative fluorine. Basically, their valence electrons are so far away from it, they don't even know like what they're doing. Basically, it's just like so far away. And they can participate in chemical reactions. So we only really see this for really large noble gases like xenon, maybe krypton, but nothing smaller than that. All right, so let's do the 6 steps for period 3 elements, our hypervalent molecules. The 6 steps still work. You just need to count very, very carefully. So SF4. So we count valence electrons. Sulfur has 6. There's 4 fluorines, so 4 times 7. 7 fluorine's a halogen. So we add that up. Can someone add that up for me? Thank you, 34. Okay, we need to count very carefully. Still the same steps. It's charge neutral, so we get those 34 electrons to spend. I'm going to put the sulfur in the middle, and I'm going to draw those fluorines around it. So how many electrons have I placed so far? 8. So now I put the next electrons on the outside, but you have to count very carefully. Because if there are any leftover electrons, where do they go? On the central atom. But that's only if there's some left over. So you need to count carefully. So 8. 8 electrons so far in bonds. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So by drawing all those 32 electrons, I completed the octets of the fluorines. I'm left with 2 extra electrons. Where do they go? On sulfur. There's the Lewis structure. This is what I mean, count carefully, because if you just kind of like blow chunk electrons all over the structure, you won't know if you have any left over to put on that central atom. Okay, so let's do BRF4 now. So you count electrons here, valence electrons again. Bromine has 7. There's 4 fluorines, each of them have 7. This is an anion, so how am I going to adjust the valence electron count? Am I going to add an electron or remove an electron? An anion is what charge? negative. So essentially we're adding an extra electron here to the count. So I can do this. This is 5 times 7 plus 1, so 36. Is that right? Okay, all right. So we have 36 electrons to spend. It's an anion, so we add an electron. We can spend an extra electron in our structure. So those are the number of valence electrons. Skeleton. So bromine goes in the middle, 4 fluorines again. 1, 2, 3, 4. So I've drawn 8 electrons already. We put electrons on outer first, then inner if there's any left over. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, so how many electrons go on bromine? 4. Yeah, so 1, 2, 3, 4. There we go. There we go. So yeah. No, it doesn't matter. And we'll learn that here in like 2 slides, that how I draw it on paper. So the question is, does it matter where I put the lone pair? No, as long as the 2 electrons are together. So I could do this technically, or I could put the electrons like here and here. That would just look weird. I don't know. I like symmetry because I'm a human. So I put it here and here. But we'll learn here in a little bit that these Lewis structures we draw don't actually represent what they look like. So even though I draw the 2 lone pairs like as far away from one another as possible, doesn't necessarily mean they look like it looks like this in real life. This molecule, right? Both of these molecules I've drawn and they're flat, right? Because I drew it on flat paper, but they actually don't look like this technically. And that's what we'll learn here next. And that's what you'll explore in molecular geometry next week. Okay, so do we like the 6 steps? They always work. It always works. All right, and so the interesting thing here is both of these molecules have 4 bonds to them, right? Like 4 fluorines attached to it, but way different environments around that central atom. And we got to be cognizant of how many electrons we place there. Okay, so I'm going to skip this slide. Yes, and this is where we're going to next. What do molecules actually look like? Electrons are not dots on a page. Even though we drew them like that in our Lewis structures, they don't technically look like that. So, you know, we could draw this molecule. We could draw I could tell you, oh yeah, draw the Lewis structure for CCl4. You would do the 6 steps. You would draw something like this. You would see, okay, yeah, I put the electrons on the outer, none go on the central atom. If you check, everything has a complete octet. How we draw this Lewis structure doesn't actually represent what these look like in real life because we are limited by 2-dimensional paper. Molecules exist in 3-dimensional space. So, you know, you look at this, you may think, because you drew it this way, oh, there's a 90-degree bond angle between those chlorines. No, there's not. We have to use what's called VSEPR theory to predict what molecules look like. Electrons are not dots on the page. They actually exist in 3 dimensions. So here's some examples. Here's a molecule with 2 bonds to it and it's linear. Here's a molecule with, again, 2 bonds to it, but it's bent. That's weird. Or here, these 3 molecules all have 3 bonds to it, but they're all completely different shapes. How do we get that? There's a method. There's another strategy to do it, but they all start with the same first thing. It's we need the Lewis structure first. We need the correct Lewis structure to predict geometry. So when talking about this, all right, one last thing is, you know, we took the formula to draw Lewis structures. We took the composition, drew the structure, all right? So here's really where the cusp between composition and structure overlap. The composition, the atoms that were given to form a compound dictate the structure, the Lewis structure we draw, and ultimately the shape that it makes. And these shapes are really important because they dictate a lot of reactivity that we see. All right, and we'll expand on that in chapter 8. Okay, so there we go. Molecules are not flat, but sometimes they are, but not always. Okay, all right, so What determines the shape of a molecule? The big idea. Electrons, they're negatively charged, and they always repel one another. They always repel one another. They're like brothers and sisters who hate each other, and they want to get as far away from one another as possible. But they are not limited to two-dimensional space. They get all of three-dimensional space to do that. So we use the theory called VSEPR theory, valence shell electron pair repulsion. Basically, what I just said, electrons repel one another. Predict the shape, understanding electrons repel one another. But the thing is, when we drew our Lewis structures, electrons existed in multiple places. They could exist in bonds, or they could exist in lone pairs. Both of those things repel one another because both of them are made of electrons. Okay, electrons, they hate each other, they repel one another, whether they are in bonds or in lone pairs. So that's what we need to understand. This is what gives us our electron domain geometry. When we consider how many total bonds and how many total lone pairs there are in a structure. And when I talk about bonding electrons, if it's a double bond or a single bond, we typically think about it as bonding domains. Both of those count as one. We'll look at some examples here. Okay, so but the thing is, if we had like a molecule like ammonia, right, NH3, we saw that there was one lone pair on it. Do we see electrons? Can you see electrons? No, but can you technically, can you see atoms? We can see where the atoms, where the bonds are. So there is electron domain geometry that considers both electron lone pairs and the bonds, while molecular geometry, basically you only think about where are the atoms at, where are the actual chemical bonds. And there's some overlap here. The electron domain geometry you get is always the template on our molecular domain. We only see atoms, we don't see lone pairs, but we do see their influence. So these are basically the parent shapes of all of the different electron domain geometries. So depending on how many total bonding and non-bonding domains there are, we get these different shapes. When you only have two domains, they will spread out as far away from one another, repel as far away, and be linear from one another, because that's the maximum distance they can get away from one another. If there's three bonding domains, it's trigonal planar. Do I have the shapes? Yeah, so here's linear. All right. Then next, if there's three total electron domains, it's trigonal planar. So each of these white balls, just think of it as like an electron domain. All right. That's how they can be all as far away from one another. What are the bond angles here between white ball to white ball? 180. How about here? 120. Very good. Do I need to explain why? It's math, I think, geometry, but I don't teach geometry. I'm not very good at that. So those ones are flat. Those are easier. All right. This is when it's 4 electron domains. This is called a tetrahedron. All right. Where there's 4 domains, all equally spaced. It would be like equivalent of like an equilateral triangle, but like in 4. So in 3 dimensions. So what's cool here, like no matter how you drop it, there will always be one ball sticking up, identical. See like that? All right. So this tetrahedron, it's special. Its bond angles are 109.5. Each bond angle, they're all identical, 109.5. All right. 5 electron domains is trigonal bipyramid. That's what this looks like. See that? See that? They're all spread out as far away as humanly possible. And then 6 electron domains is an octahedral. An octahedral. All the bond angles here, can you see it? What do we think it is? All 90 degrees. Yeah, 90, or if you look from here to here, it's 180. All right, so there's that. Okay, those are electron domain geometries. So you need to memorize these names and these bond angles. So here they all are. It's the same stuff, but you already know most of these. I showed you the shape and you're like, oh yeah, those are 90 degrees. Like, yeah. Okay, so think about it spatially. Think about it spatially. So do memorize the bond angles and the names here. I like just to think electrons, they hate each other. They're gonna spread out as far as possible. All right, and then there's, geometry that'll dictate that. Those are all our electron domain geometries. But the thing is if I have an electron geometry of tetrahedral, not all of these need to be atoms. Some of them could be lone pairs. And then that's where we get molecular geometries, where some of them are lone pairs, some of them are bonds. So the shapes change, not really change. They're not changing. The template is not changing. It's just the name changes because, again, we can only see atoms. We can't see lone pairs. So this table is much more intense, but it's actually the same table as the previous one. It's the same exact table where in this column, these are all what I call the parent electron geometries where there's 0 lone pairs. So if you do have a structure that has 4 bonding domains and 0 non-bonding domains, you would get a tetrahedral, right? That's what the molecular and the electron geometry would look like. But things start getting complicated once there are lone pairs on the structure. So basically, for example, here, if we took something that's trigonal planar, that's the template, electron template we start with, but one of the electron domains is a lone pair and 2 are bonding domains, we cannot see this lone pair. We cannot see that. So what I like to do is think, okay, if I erase that lone pair, what shape is left over? That XEX, what is that? That is a what kind of shape? Bent shape, right? We cannot see that lone pair, but we see its influence. Or same thing with a tetrahedral. If we add a lone pair to a tetrahedral, we can't see that lone pair. So we talk about what shape is left over when you squint your eyes and remove that lone pair. It's a trigonal pyramid is left over. Or in this one where there's 2 lone pairs, oh, we need to erase both of those lone pairs, okay? And then we think about what shape is left. It's bent again, but it's bent with a different bond angle, right? So that's the big idea here. I like to just memorize the parent geometries and then kind of just use my intuition and start covering up places if we have lone pairs present. So I want to do some examples. Oh, okay, wait, here are my steps. There are my steps, then we'll do the example. So steps to determining a molecule's geometry. First, you need to draw the Lewis structure. So that means do 6 steps. I know, we just learned that like 20 minutes ago. Okay, then it's use Vesper theory. We focus on the central atom, or like some atom, we focus on one atom and we count the number of bonding electron domains. So we're counting bonding domains and non-bonding domains. Then that tells us how much the electrons need to spread out, the electron domains spread out. Then finally, take into account any lone pairs that are present, and then that will describe the molecular geometry because we can only see atoms, we can't see lone pairs. Okay, so let's do some practice. All of these I already give you, okay, write it. I already give you the Lewis structures because I don't want to see you struggle too much. But you do need to practice Lewis structures. Okay, so like when you all like tell me in your surveys, like tell me what I need to memorize. Memorize how to figure out valence electrons. Memorize the 6 steps, but know how to use the 6 steps to get to Lewis structures. And absolutely memorize those tables, those geometry tables. Okay, so here are all the Lewis, I give you the Lewis structure. So we want to focus on just the central atom and think about what that looks like, all right? So electron geometry, we count bonding domains and non-bonding domains. So look at that nitrogen. How many total electron domains are around it? 1, 2, 3, and then does that lone pair count as a domain? Yes, it does. So there are 4 electron domains around that nitrogen. So go to the table. What does 4 electron domains mean? Or just think, okay, if I have 4 regions of electrons, how will they orient themselves to be as far away as possible from one another? A tetrahedral. So this is the one we're talking about. This is its electron domain geometry. So it's a tetrahedral. I'm going to draw it in 3 dimensions. All right. I'm not that good of a drawer, but whatever. It's going to look like this, where that wedge means that there's a bond coming out of the page, and then the dash means a bond is going into the page. Do you see the tetrahedron? Yeah, it's a good picture, isn't it? Okay, so all of that picture, this picture is depicting anywhere I find electrons, lone pair or bonding pair, right? That's the electron geometry. Molecular geometry, we only focus on the bonds themselves. So I like to think to myself, how many of those domains are lone pairs? How many? Just one lone pair I need to consider. So I need to draw that lone pair on there, on my electron geometry template. So I'm just going to draw it right here. There's my lone pair. See it? Okay. Can we see that lone pair? No, we only see atoms. We only see the atoms themselves on the ends, you know, of these bonds here. So oftentimes what I like to do is like just erase the lone pair and think to myself, what shape is left over? So if I erase it like that, what shape is left over? It's a triangle, but it's kind of raised, so it looks like a pyramid. It's not flat, right? It's not trigonal planar. It's not trigonal flat, but it's trigonal raised up. It's trigonal pyramidal. So this is the shape of ammonia. It's trigonal pyramidal. Okay, do you see that? All right. So there it is. So then the name here is trigonal pyramid. All right, so let's do the next one, CH4. So there's the Lewis structure. How many electron domains around that central carbon? 1, 2, 3, 4. Very good, 4. So what's the electron geometry? Tetrahedral again, same thing. So I'm going to draw the tetrahedron. So boop, 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 boop. Do I need any lone pairs to worry about? No. So what's the molecular geometry? The same thing, because we can see every single domain. Every domain has an atom on it, and we can see that. So molecular geometry is tetrahedral. All right, next one. Ozone. So note here, a double bond, a triple bond, a single bond, they all count as one domain. So if our central atom is this oxygen, this double bond is one domain, the single bond is one domain, and that lone pair is one domain. All right, so don't double count the double bond. I like to think of it as, okay, yeah, in that double bond, there's 4 electrons in there, but they're all squished in the same place. So they're all gonna just move together, right? They're not gonna like move apart from one another. So how many electron domains is that? Did I just draw? I highlighted in pink, yes, 3. So 3, what is 3 electron domains? If you have 3, if you and your 2 brothers want to get as far away from one another as possible, what angles are you going to orient yourselves? 120 degrees, right? And form yourself into a trigonal planar arrangement. So this is trigonal planar. And so I'll draw it. I don't have to draw in 3 dimensions at this time. All right, that looks really bad. Where you have ideal bond angles of 120 degrees. Ideal. Okay, but that's the electron geometry. Can we see every single domain? No, because one of them is a lone pair. So I'm going to draw that lone pair. I think I need to redraw this. So go boop, boop, boop. Okay, so I'm going to draw that lone pair right here. Okay, we can't see that. So I'm just going to erase it and think to myself, what shape is left over? Bent. We have this bent structure left. So ozone is a bent shape. And you can kind of see it in the Lewis structure. I tried to pick Lewis structures where the shape, how it was drawn, doesn't represent what it looks like in its molecular geometry, because I am mean like that. So that's bent. Okay. All right, last one, SF4. Oh no, there's another page. Geez. Okay. How many electron domains? 1, 2, 3, 4, 5. So 5 is, if you look at the table, trigonal by pyramid. All right, and so for funsies here, this might be difficult to see. So this is a trigonal bipyramid. There's 2 atoms that go up and down here, and then 3 kind of along the belt region here. So if you look at this structure, there's 1 lone pair we have to consider. So if you are a big, juicy electron lone pair. And you have the choice to go here, where you are 90 degrees from other atoms. Remember, you're big, fat, and juicy. Or if you want to go here, where are you going to go? On this belt region or at the top here. So these bond angles are 90 degrees. The ones down here, if you look down the center, what are these bond angles? 120. So where are you going to go? Are you going to go in the what we call the axial position? So if it's like a top, you know, so axial position or equatorial position, where are you going to go? The equatorial position, because there's more room there. And that's what you see in the structure. See how that lone pair is kind of in that equatorial position. So that's what happens here. This is what trigonal bipyramid looks like in 3 dimensions, like that. Okay, one of those is a lone pair. So I'm just going to say it's this one right there. That's in the equatorial position. And when you erase that and you ask yourself what shape is left over, what does that look like? Put it on its side. It's a seesaw. And that's literally what it's named, because chemists aren't creative. It's a seesaw. All right. Okay, there we go. All right, let's keep going. Water, electron domains, 4. So the geometry there is tetrahedral. So same thing as ammonia and CH4. So when I draw the ammonia molecule, tetrahedron, based upon the Lewis structure, how many electron domains are lone pairs? 2. So I need to draw 2 lone pairs here. Doesn't matter where. I'm going to just say this one is a lone pair and that one is a lone pair. Right? And so to get the molecular geometry, I erase the lone pairs and ask myself what shape is left over. Bent. Yes, it is bent. The common mistake that students do when going from electron geometry to molecular geometry is that they forget about the influence of the lone pairs. I will oftentimes see this. I'll see, oh, water's electron geometry is tetrahedral. They'll get that right. They'll count 4, but then they count, oh, but there's only 2 bonds. So that's a molecular geometry of 2. So that's linear. They'll say molecular geometry is linear. The thing is that molecular geometry has to template on the electron geometry. The electrons are still there. We just can't see them, but we do see their influence. So do not be that person that says, oh, yeah, water is tetrahedral and then it's linear. Or they'll look at ammonia and they'll say, oh, electron geometry is tetrahedral once you put on, but it has 3 bonding domains, so it's trigonal planar. They'll say that. They'll say trigonal planar. But those 2 shapes do not template on one another. See that? Okay. All right. So let's keep going. Okay. So nitrate. Molecular geometry. What is it? Are there any lone pairs? No. So electron geometry is 3. So molecular geometry is also 3. So this would be trigonal planar. Because remember, a double bond is 1 domain, a single bond is 1 domain. All right. BF3. I drew it T-shaped. Is BF3 T-shaped? No, it's not. No, it's not. So BF3 has 3 electron domains. Does it have any lone pairs? 0 lone pairs. So it actually has the exact same geometry as nitrate. It's trigonal planar. All right. How many electron domains on SF6? 6. Any lone pairs? No. So 0 lone pairs. So it's molecular geometry and electron geometry match because there's no lone pairs to consider. So this would be octahedral. Cool. So do practice those. Do practice them. Bond angles too. Okay. So because I could look at these and we already looked at some of them, right? And thought about bond angles and all that, you know, like we start with a tetrahedral, or no, let's not do that. Let's start with a trigonal planar, see, like that. So what are the bond angles here? 120, great. Then so this is like my electron geometry of 3. trigonal planar. If we have one lone pair, right, I just cover up this spot, but we are still left with the atoms in this arrangement. What would we call this arrangement? Ben, is this bond still 120 degrees? Yes, there's actually small deviations. So deviations from ideal geometries. These are lone pairs. So the bond angles are only exactly 120 degrees when everything is a atom. Once we start putting lone pairs in there, it deviates a little bit, but this will get you through it. As long as you know that electrons, lone pairs, they're big, fat, and juicy, and they just take up more room, and they push other bonds to be closer to one another. That's essentially all you need to know. So when we have our ideal trigonal planar, it's 120 degrees. But when we put a lone pair right here and it takes up more room, it's going to push these bonds together a little bit closer. So you're more likely to measure a bond angle of like 118. So it just deviates a tiny, tiny bit. That's it. All right. So that's the big idea here, that lone pairs take up more space than a bond. Lone pairs repel or push bond angles away from ideal. So here's another example, methane, so CH4. All of those hydrogens are identical. So they're not pushing any more than any other bond. The bond angles in methane are exactly 109.5. But in ammonia, still tetrahedral electron geometry, but there's a lone pair. That lone pair is big and fat. It's going to push everything closer together. So the bond angles in ammonia are 107. And then water, the most extreme of them, have two big fat lone pairs, and it just pushes the bonds a little bit closer together, right? And so here it's 104.5. All right, so just deviated a little bit from 109.5. Okay, so let's think about this molecule. Let's see if we can't get the bond angle between the chlorine, carbon, chlorine. So just based upon the structure, what is the ideal bond angles around that carbon atom? What's the ideal bond angles? So you might need to think about, okay, what is the geometry? It's an electron domain of 3, 0 lone pairs. So that is a trigonal planar. So it's still this one. So the ideal bond angles are 120 degrees. Okay, so we said that lone pairs are big, fat, and juicy and just take up more space. So what do you think takes up more space? A single bond or a double bond? A single bond has how many electrons in it? 2. A double bond has how many electrons in it? 4. So which one repels more? The double bond. So like for the same reason, when we have a lone pair present, a double bond also will just take up more space and push these bonds closer together. So when considering that little blue angle, are you going to measure a bond angle of exactly 120 degrees? No. Is it going to be more than 120 degrees? No, it's going to be slightly less than 120 degrees. There we go. Cool. Yes. All right. Very good. All right. Skip to slide 45, I say. Okay. Yeah, let's do this one. So let's predict the bond angles in this molecule. I did not draw it to represent what its geometry looks like. So we actually have to do the work here. So my strategy here is look at each bond, identify the central atom, determine the ideal bond angle, then consider any deviations from that. So let's work left to right. So let's focus on that oxygen first. That oxygen has how many electron domains? 4. 4 electron domains. So what shape is that? It's a tetrahedral. The ideal bond angles in a tetrahedral is what? 109.5. But is this going to be a perfect tetrahedron? No, because it has lone pairs on it. So what do you think we will measure here? Exactly 109.5, bigger than 109.5, or smaller than 109.5? Smaller, yeah, because those two lone pairs are essentially going to push the bond angle closer together. So we're going to see a bond angle smaller than 109.5. I'm just going to put 2 of them because there's 2 lone pairs. So it's going to be smaller than 109.5. A student who doesn't consider you know, electrons repelling one another, if they just think electrons are dots on a page, they will say 180 degrees. Do you see how they get 180? And you laugh, but you might make the mistake, right? How I draw it doesn't necessarily mean what it looks like. And we have to apply Vesper theory. Because doesn't that look, you'd be like, yeah, that's 180 degrees. But the bonds don't adopt that shape in 3 dimensions. Okay, this carbon, what's its electron geometry? It has how many domains? 3. Because that double bond counts as 1, so that is a trigonal planar. Trigonal planar's ideal bond angle is 120 degrees, but are there any deviations present that might mess up at 120? Yes, that double bond. So the question is it going to be more than 120 or less than 120? Less? More, yeah. So if I redraw it, okay, so like that, I'm asking for this bond angle right there. So it's actually going to be more than 120. All right. And so bond angle 3, it's kind of the same thing where it's 3 electron domains, trigonal planar, ideal is 120 degrees, but based upon where the angle marker is here, is it going to be more or less than 120? This time it's less than 120. Because it's opposite. It's opposite of where that double bond is. So in that one, this third one, excuse me, it's asking for that bond angle. So the double bond is going to push more away. I like questions like this because it really requires you to know how to, you know, look at a get your Lewis structure, understand Vesper theory, apply ideal bond angles, and then finally small deviations to those bond angles. Okay. How much time do we have left? 7 minutes. Okay. Okay. I'm going to skip 5 and 6 electron domains. I actually want to talk about molecule polarity. So molecule polarity is important because remember, molecules exist in 3 dimensions. And so whether we can predict something is polar or non-polar or not, we want to think about vectors. See, I'm not good at math. Like you guys know vectors, like that's like sines and cosines and stuff. Yeah, I'm not that smart, so I don't do that. So we're just gonna look at a very superficial use of vectors to figure out, okay, if we have atoms in 3 dimensions, and each of those atoms are pulling on electrons differently, the pool of electrons differently on a 3-dimensional structure might involve or might cancel out vectors in 3 dimensions. So I'm showing 2 different molecules here. CO2, right? This carbon is being pulled by each of these oxygens, right? Like there's a lot more electrons on these oxygens than the carbons. We skipped these parts, but that's all you really need to know here. But how those oxygens are arranged to one another, that carbon, if both of those oxygens are pulling on it at 180 degrees at equal strengths, because it's the same atom, those vectors cancel out in 3 dimensions. How I get my 1210 to understand this is called, my method is called babies versus bodybuilders. All right. So if you think of carbon as a tire, each of those oxygens, they're big, they're 2 bodybuilders pulling on that tire at the same time, 180 degrees from one another. They both pull at the same time. Will the tire move at all if they're both equal strength? No, they won't. But what if I put a baby on one side and a bodybuilder on the other side, 180 degrees from one another? Would the tire move? Yes, it would. So that is an example where the vectors do not cancel in 3 dimensions. That's all we care about as chemists. Do they cancel or not? So in this example where it's oxygen, oxygen, do the vectors cancel? Yes, but what about water? This oxygen, that's my tire. Here are my 2 babies pulling on the tire at the same time, but they're not 180 degrees from one another. They are, you know, like 100 109 or whatever, 104 degrees away from one another. So if I have two babies pulling it on at the same time, will the vectors cancel out? No, it won't. So water is a polar molecule. That's all we need to know, okay, in terms of vectors. So if we want to answer these, both of these molecules contain polar covalent bonds, but only one of them is polar. It's H2O. CO2 contains polar bonds, but because they cancel in 3 dimensions, the molecule's overall nonpolar. Babies versus bodybuilders works just for conceptualizing vectors, so we don't actually have to calculate anything. All right, okay, so if vectors cancel in 3 dimensions, it's nonpolar. If it does not cancel, it is a polar molecule. That's all we care about. So let's look at these molecules. Are they polar or not? So I have them here. CO2, is it polar or not? Not. So what, I see head shaking and nodding. Sorry, is it polar or not polar? Non-polar, very good. What if I drew it like this? What if it was carbon, oxygen, sulfur? What about that? Polar, yeah, because we have a bodybuilder on one side and a baby on the other side. And if you have them pull at the same time, will the tire move? Will the vectors cancel? All right, the vectors will not cancel. All right, that the tire will move in space, so it's polar. This would be polar. I didn't draw the lone pairs. All right, BF3. So see the arrangement. They're all 108, 120 degrees from one another. Polar or not polar? Non-polar, yeah. So now we have three bodybuilders all pulling on that boron at the same time. They just so happen to be 120 degrees. They all cancel. What about NO2 minus? So here, that nitrogen is our the tire per se. We have a lone pair around 120 degrees. Does this cancel? The vectors cancel here? No. So this would be what kind of molecule? Polar. Yes, great. What about CH4? Polar or non-polar? Non-polar, yeah. All of those bonds are 109.5 degrees. They're going to cancel. What about ammonia? What about ammonia? That lone pair is going to fudge everything up. Okay, it's going to fudge up those vectors. So this would be polar. What about water? We already did water. It's polar. Okay, those lone pairs always mess things up. And then this is the point when students ask me, when there's a lone pair, that always means it's polar, right? And I go, and then we keep going. Okay, what about PCl5? So note where these bonds are, polar or non-polar? Non-polar, yeah, because these two bonds, these two cancel each other out, and then there's 3 along the equatorial cancel each other out. Okay, what about SF4? Here's a lone pair. Polar or non-polar? Polar, yeah. Once you disrupt symmetry, it's all messed up. Okay, CLF3, polar or non-polar? Polar, yeah, because again, those lone pairs fudge everything up. What about this molecule? Non-polar, you guys are good. You're good. Babies and bodybuilders work. It works. Okay, let's keep going. Octahedral, polar or non-polar? Non-polar, okay. Square pyramid. What do you think? Polar, yeah, because that lone pair. What about square planar? Non-polar, yeah, because the two lone, see, this is what I show the students. I go, oh, look, but these two lone pairs cancel one another and it's non-polar. All right, that's it. Good, that's exactly where I wanted to stop. That's enough for you to get through molecular geometry next week. Oh, so this week only, I actually already changed the due date, only the first part of chapter 6 is due. So that means next week you'll probably have like 3 homework sets due. Yeah, so I'll just give you a break. Oh yeah, wave or particle? Wave or particle?
particle. Yeah. I want to be a beefy
I thought all you
particle.
guys like classical physics. I thought you were all classical people. What?
I think it's gonna be a landslide.
Just like the Chiefs? Or no, everyone voted for the Eagles, and we saw how that went.
I want to be a particle. I don't know. I feel like at our age, we should all be waiting. Just don't want to go in.
Oh, girl, that's nice. That's real nice. Okay. You guys are funny.
Can you look away so